And here we go again. We are on day 17 of our Calculus AB adventure, and now is really where we get rolling on these derivative rules, right? And it's not that the derivative rules, like, yeah, man, awesome. It's the rules of derivatives. So we already know one rule and a couple little corollaries, that one rule being the power rule. But really for today on out, we're going to get at least one more new rule every single day. And all of these rules are just working together to make sure that we don't need to use limits and we don't need to go a long way around when there's a faster way to calculate a derivative and really a derivative function. So let's get to it. Last class we had you try to take the derivative of this function, 2x plus 5 times 3x squared minus 5. And you might have gone the wrong way about it and done the derivative of 2x plus 5, which is just 2, and then 3x squared minus 5, which is 6x, and then multiplied and said, ha, we're done. But then we dropped that knowledge bomb on you of saying, well, wait, if there's multiplication in between two sets of terms that each contain an x, two sets of factors in this case, you can't do that. We don't have a rule yet for derivatives with multiplication in between. What we're going to do right now is actually derive or determine a new rule that is called the product rule. And of course, remember, the product of two numbers is like the multiplication of two numbers. So this is the multiplication of two factors. We're going to come up with a multiplication or a product rule that will allow us to take derivatives without having to multiply everything out first and then take a derivative. How do we do this? We're going to start with a function that I'm going to call y of x, or just y if you want. And we're going to say it's made up of two unknown functions, f of x and g of x. So who knows, maybe f of x is like e to the x and g of x is sine of x, or maybe f of x is x squared and g of x is x, or heck, even maybe 2x plus 5 is like f of x and 3x squared minus 5 is g of x. Regardless, they're functions of x that each have x in them and they are multiplying together. To find any derivative, we can always go back to our definition of derivative, right? And this is our definition of derivative using limits. What does that look like? Well, we take our function and we say we find the limit as h approaches 0 of y of x plus h minus y of x all divided by h. Let's go ahead and actually use that. So our x plus h is going to get substituted into our function here. So we have the limit as h approaches 0, and the y of x plus h is going to take that spot. Here's going to be y of x. I think y of x is pretty easy. That's just f of x times g of x. That's the name of our function. And the other one is f of x plus h times g of x plus h. So this is y of x plus h minus y of x, and all of that is divided by h. Well, does that actually help us? If we replace the h's with 0, then we get f of x times g of x minus f of x times g of x, that's 0 on the top, and on the denominator we also get 0. 0 over 0, indeterminate, drat. Now this shouldn't shock you because really every single limit we set up using the definition of the derivative will be indeterminate. We're going to have to use some algebraic trick to simplify it. Now this algebraic trick is probably a new one for you, and it's very clever. It's also a really common trick when you're trying to prove different identities and you go, but I only have two terms, I need way more to work with. Well, it's the same thing here. There is no like term between these two. We have an f of x plus h and an f of x, but they're not like each other. So what we're going to do is add what's known as a zero pair. In particular, we have this f of x plus h times g of x plus h, that's up above, and we have this minus f of x times g of x, that's up above, but this zero pair is a minus f of x plus h times g of x and a plus f of x plus h times g of x. Because of course if you combine like terms here, these are like terms, they cancel out. A negative version and a positive version, they're exactly the same, one negative, one positive. That's like adding 0, and you can always add 0, right? If I gave you $10 and took away $10, it doesn't change how much money you have. I'm maybe being mean by doing that, but it's the same thing here. The reason that we're doing this now is because we introduced some common like terms that we can factor out. So let's find out what's in common for the first two terms. So the limit as h approaches 0, my first two terms are these two. Well, I see in those two, I think I see that they each have an f of x plus h. I'm going to factor that out. So it's going to be f of x plus h times, and then in the interior I still have g of x plus h, right? That's right here, minus, don't forget the minus sign, and then there's still this little g of x hanging out like, hello, I'm still here. Okay, all right, plus, now we'll do the same thing on the other side. On the other side, let's see, what do we have in common here? I think we have a g of x in common here, so we'll factor out that g of x and say, okay, well, what do we have left inside? Well, we have an f of x plus h and a minus f of x. All of this still, of course, being divided by h. Now, from here, we're actually going to split our limit into 4 smaller pieces. And these 4 smaller pieces take a little bit of getting used to, but I think you're going to be okay. So ultimately what we have here is one giant term plus another giant term. And they're both over h. So what we can do is we can, of course, split, and I probably should have done 2 different colors here. Let's do this one in blue. We can split this fraction into 2 smaller fractions that are both divided by h. So one of those fractions is right here, f of x plus h times g of x plus h minus g of x. And the other one is over here, g of x times the whole quantity f of x plus h minus f of x. And that's all over h. Now you're saying, well, it's not really all over h. There's probably a step in the middle. So what I'm going to show right here is just how I split part of this, and then the rest should become fairly apparent. And I'll show this over here. So it's the limit as h approaches 0 of, and I'm just going to write this as f of x plus h over 1 times g of x plus h, maybe in parentheses, minus g of x over h. And wouldn't you agree that this fraction multiplication is this exact same thing right here? Because, of course, when you multiply fractions, you multiply straight across. And so that is really all we wrote down here. Technically, this is over 1. You multiply fractions together. It's still the same thing. We just split them into smaller pieces. We need to keep the plus down here, and then we did the same thing in blue. Okay, well, how did that help us? Well, when working with limits, it's always easy to make the limits a little bit smaller so that we have smaller pieces. So, of course, we're going to go ahead and try to see what happens when we replace all of our h's with 0. So, our first one, if we replace h with 0, it just becomes f of x. Here, if you replace h with 0, well, I think we get g of x minus g of x divided by h. But wait. This limit should look really familiar to you. This limit is the definition of the derivative. That's actually what we started with right up here. It's our definition of the derivative, but it's our definition of the derivative using the function g. And what does the definition of the derivative find us? What does this limit find? This limit finds g prime of x. That's the whole point of using this limit definition. It finds g prime of x. So we're not really reducing this. We just need to know it's our definition that finds the derivative. Plus, well, there's nothing even to plug h into here. There's no 0 or nothing to plug 0 into. It's just g of x. And then this last part, let's take a look over here. Definition of the derivative again. This is f prime of x. And that's pretty nifty. We were able to go through and take these crazy limits and simplify it down to a pretty simple looking little expression. This is the product rule, sometimes known as the derivative of products. And it's missing a little parenthesis here. Whoops. Sometimes you will see the product rule written as d dx, take the derivative of 2 functions multiplying together. And when you take the derivative of 2 functions multiplying together, this is the formula. And the shorthand for this is to leave off the function notation and just say f times g prime plus g times f prime. I actually like to rewrite this a little bit differently. So I'm going to say it like this. I'm going to say if we have f times g and we want to take the derivative of that. Sometimes you'll see the prime of f times g, the first derivative of that. I really like to write it like this. I like to take this term and put it in front, and I like to write the f prime first. So f prime times g plus, and then I like to write this term second, plus f times g prime. Why do I like it this way? Well, first, I like that it maintains the order of the original functions. F always comes first in each of the terms, each of the pairs if you want. G, of course, always comes second. The second reason I like it is because it makes it a little easy for me to remember. When you do the derivative, you do the derivative of the first function first, keep the second the same. And then in the second set, you do the derivative of the second one second and keep the first one the same. Last but not least, when we learn our quotient rule, our division rule, because we only know multiplication right now, when we learn our division rule next class, if you write it this way, you don't have to change the order for the division rule. There's a couple other things that add on, but I love being able to keep the order the same instead of having to memorize two different orders. I've actually, pretty much every textbook writes it in a different order. I think they do the one up here. I've always done it this way. So if you want a different order, if you watch a different video, it gives a different order, that's fine. You still get the right answer. As long as you combine a derivative of one and a regular equation of the other, you're good to go. You should also realize the product rule can be applied to more than two functions. Let's say you had like e to the x times sine of x times x squared. That's three functions. Well, if you take the derivative of three functions, it's the same idea. You do the derivative of the first one first, keep the other two the same. Then you do the derivative of the second one second, keep the other two the same. Derivative of the third one third, keep the other two the same. And the order is exactly the same this way, right? If you didn't have an h in here, there's your product rule. So nothing too terrible. In fact, we could even do it for the four functions multiplying if you wanted. Now, you really never get asked with three functions or four functions multiplying. It's just kind of cool to play with the pattern. So I bet you'd realize there's probably four terms, and we'd write out f, g, h, and I in each one of these four terms. So one, two, oops, I'm already switching things around. Multitasking is not easy for me. Distracted listening is probably a better way to call it. And then we just put in our terms. So in the first term of four functions multiplying, we need the derivative of the first function, second function, third function, fourth function. Easy enough. Product rule. Now, we've been doing this general product rule with no function, so we should probably practice this. Okay. For each set of functions multiplying, do the problem once using the product rule and once without the product rule. Try to get the answers to match each other. Then evaluate which way was faster. Okay, well, let's look at a couple of these and then you guys can get some practice in. d dx of x squared times e to the x. I'm a big fan of rewriting the actual product rule first. It's totally up to you, but I think it really helps out, especially the first couple times that you do this. So d dx of, and let's do our product rule, f times g is going to be f prime times g, derivative of the first, keep the second the same, keep the first the same times the derivative of the second. And then directly below it, I rewrite the actual problem. Right? And maybe I should actually use some colors here to keep everything straight. So I'll do the function f in purple and the function g in green. Okay, so if the first thing we're going to have to do, oops, I don't know why I wrote f and g, that was silly. X squared is going to be my first function and g is going to be e to the x. Here we go. X squared. Well, we have to do the derivative of f first. So the derivative of x squared is 2x. I suggest, by the way, putting each of these terms in parentheses. I'm a big parentheses user. You're not going to go wrong using more parentheses, but you might go wrong if you leave off parentheses. And then g means just keep g the same. So it is e to the x plus. Now go back to your original f equation, which was x squared, keep that the same, and take the derivative of g. Well, don't forget, the derivative of e to the x is really easy. It's just itself, so it stays e to the x. And that's it. That's your derivative. You're done. I will tell you that your textbook will probably rewrite this. Your textbook as an answer will probably factor out this e to the x and keep the x squared and 2x inside. You get full credit for what I just boxed. but you also get full credit for this. Either one is okay. However, for your independent practice, for good algebra practice, you should strive to match the answers in the back of the book, or if you're looking at my solutions, try to match my solutions too. The more algebra you practice, the more it becomes second nature. Again, if this was a free response, you'd want to stop as early as possible. No reason to go any further. However, some multiple choice answers will simplify further than you're used to, and if you don't do it, you won't know how to think through that. So, there's that. Cool. Well, what did we mean by not using the product rule, right? Once without the product rule? Well, let's try this one over here. It says take the derivative of x squared times e to the x. Well, actually, I don't know how to take the derivative of that without the product rule. We can't just say that this is 2x, that's the derivative of x squared, and we can't say this is e to the x, that's the derivative of e to the x. That's not it. That clearly is not this answer, which is correct. You can't do the derivative of each piece individually. You have to use the product rule. There's no other way that I know of to do this problem. So that's that. There's our product rule. Let's try one more, and then I'm going to have you, actually, if anytime you're comfortable, go ahead and pause this and work on ahead. But let's try one more. Product rule. Let's see, how do we do this? Product rule, product rule, product rule. I'll do the same thing as I did before. I'm going to write out our two functions here. The more you write it, the more you're going to get used to it. There is no formula sheet for AP Calculus, and there are a decent number of formulas, so the more you use them, the more you're going to get used to it. Derivative of the first, keep the second the same. Keep the first the same, derivative of the second function second. Okay, well, the problem is I'm not quite sure what f and g are here. Of course, we might remember that when you have something squared, you can of course write it times itself, 3x minus 2 times 3x minus 2, and then maybe it becomes clear of what your f and g functions are. I think we're going to have to write pretty small here, so stay with me. d dx, our first function, I'll do in blue, is 3x minus 2, and my second function is 3x minus 2. Okay, well that's going to be equal to f prime, so the derivative of f, the derivative of 3x minus 2, derivative of 3x is 3, derivative of negative 2 is 0, I think it's just 3, that's pretty nice. Keep g the same, I can do that, plus keep f the same, that was 3x minus 2, and then multiply by g prime, well, 3, that's the derivative we did before, it's just 3. And you're done. That's your final answer. Of course, you could simplify further if you wanted, and I'm going to. We should realize that we have 3 of these 3x minus 2's, and if you'd written this 3 out front over here, you'd have 3 more of them. So in total, I think we have 6 of these 3x minus 2's, and that's probably as simple as you're going to get. Now, can we do this one without the product rule? Well, yes, actually, I think we can. And the way we do it, of course, is we start with, I'll need a little more room here, we start with the expanded form. So we start with 3x minus 2 times itself, and then we multiply everything out. When you multiply everything out, you'll get 9x squared minus 6 minus 12x plus 4. That's already a bunch of work, probably more than the product rule. And then you have to take the derivative of everything. The derivative of 9x squared is 18x. Derivative of negative 12x is negative 12. The derivative of 4 is 0. That looks pretty good. Is there anything they have in common, though? Yeah, I think they each have a 6 in common. And that is where we get this same answer. So 2 different ways to do it, and that means that you don't always have to use the product rule. In fact, there are going to be many problems where you have multiple approaches to it, and no one is the only correct way. Whatever way works for you. Today I'd suggest that you practice the product rule because that's the point of today, and then once you get really comfortable with it, then you can start choosing which method of attack you'd like to use. Let's look at a couple more. DDT of this problem. Well, this is weird because I see a function up here with t and another one down here, but they're being divided, not multiplied. However, you might remember from last class that we can rewrite this as 3t to the 16th minus 4 times t to the negative 6th, right? We can bring that up as long as we group the numerator in parentheses. Okay. Think we can do this without writing out the product rule? I bet we can. So I'll still keep my colors though. We'll do 1 here and 1 over here. Let's start with the first one. Derivative of 3t to the 16th minus 4. We have to do 16 times 3. I think that's 48. So we have 48 t to the 15th. Derivative of negative 4 is just 0. Keep the second one the same. That is t to the negative 6th. Plus, now keep the first one the same. 3t to the 16th minus 4 times t to the negative 6. Well, negative 6 comes down. T, and then we reduce the power, make the power smaller. I see a lot of people go the wrong way with that and end up here. Can we clean this up further? Well, sure, we could, but maybe not. I don't know. So let's hold off there, and let's just see if my answer over here matches, because we have a couple different ways to do it, and I'll try to remind you. When we work over here, one option is that you could distribute this t to the negative 6th inside and reduce the powers. But the other option that I see people forget, which is why I wanted to bring it to your attention, is we can go through and rewrite this, oops, not ddx, ddt as two separate fractions, right? 3t to the 16th divided by t to the 6th minus 4 divided by t to the 6th. Okay. And then we can reduce from here, where 6 and 16 is, I think, going to give us 10. And this one, well, we can't reduce too much, but I bet we could bring it up. So we could maybe treat this, and I'll do this down below, we could treat this as d dt of, and it becomes 3t to the 10th minus 4t to the negative 6. We have to bring this up, right? And we're here. Once we're here, then I think we could probably go through and just do our straight derivative. Now, some people really go down the product rule rabbit hole, if you will, and they say, ooh, 3 is multiplying times t to the 10th. I'm going to use the product rule. Well, you can. That's fine. But do you have to? No, 3 is just a constant, and we know with constants, we just keep it there. The 10 multiplies by the 3, that's 30 t to the 9th. And then this negative 6 comes down with the negative 4 is positive 24t reduced by 1 to the negative 7th. And that looks good. Now, a little algebra practice. Do these two look the same to you? Because they don't to me right now. How do we make them the same? Well, I think maybe we should go through, at least for this one, I think we can clean this up because we have the same bases in here, and with the same base you add the exponents. So this is giving me 48, 15 plus negative 6 is 15 to the 9th. I'm sorry, it's t to the 9th. Oof. Speaking is hard. And then I'm probably going to go through and distribute this over here. Let's see what happens. So same base again. 16 minus 7. Oh, that's also 9. That's exciting. And there's a 3 in here that's going to multiply by negative 6. So I think that's going to be negative 18t to the 9th. And then last but not least, we have this negative 4 times negative 6t to the negative 7th. That's plus 24t to the negative 7th. We're getting closer now. Look, we matched over here. My guess is there's just some like terms to take care of, and I think there are. We have 48 of something, and we're taking away 18, and guess what? 48 minus 18, that is indeed 30t to the 9th plus 24t to the negative 7th. And we end up here. Matchy, matchy. Again, you probably wouldn't have to match. In fact, with the product rule, you could have stopped right here. It's very nice. On this case, it might have actually been easier to do it without the product rule. One more, though. ddx of 9 over x to the 5th. Okay, well, product rule, that's what this left column is for, I think. So we should probably rewrite this so there's actually a product here instead of division. And to do that, we bring x to the 5th up, but change the power. Now, I am going to rewrite this one more time so that we can work underneath. ddx of 9, here's our function f, times x to the negative 5th. Well, f and g here we go. The derivative of f, the derivative of 9, is 0. It's a constant, right? And the derivative of a constant is 0. We're treating this as its own function. Forget that it's a constant multiplying. It's all by itself. It's like if I said, what's the derivative of 9? You're like, oh, the slope of the graph of 9 is 0. So the derivative of 9 is 0, and x to the negative 5th stays the same. All right. Then we keep the original function the same, and we do the derivative of the second one, and that's negative 5x to the negative 6th. Something like that. Can we clean this up? Well, 0 times anything is 0. 9 times negative 5 is, of course, negative 45. And then this x to the negative 6 negative exponents, ew, goodbye, go to the denominator, and that becomes x to the 6. Right? We didn't bring the 45. That didn't have a negative 6 exponent. These all have exponents of 1. And we end up with this guy. However, that was a completely unnecessary product rule. I'm a very firm believer if you can do problems in any way, don't do the problem that way. That takes too long. Be intelligent about this. And that really just means bring up that x to the 5th and then realize that this is a constant times a power function, right? It's a constant times a function, and we've never needed a product rule to do that. We've been doing this for a couple days now. To do the derivative, just bring the negative 5 out front, that's our power rule, and reduce the power by 1. Negative 45 divided by x to the 6th. Ta-da! Easy. Way faster. I see a lot of people start to use the product rule here. You don't need the product rule with the constant. Can you do it? Sure. Is it more work than it's worth? Definitely. Now that we've gotten some practice with the product rule, we're going to expand our knowledge of e to the x. And this is actually a pretty easy one. So we know the derivative of y equals e to the x is y prime equals e to the x. This is that really cool function where the derivative is itself. We also do need to be comfortable with something like a constant times e to the x, and we can actually find that derivative in two ways. So let's do exactly what I told you not to do. Let's do it with the product rule first. So let's say that y is equal to, we'll use some nice colors here, 5 times e to the x, and then let's find y prime. Well, the derivative of the first, keep the second the same. I missed my parentheses. And then keep the first the same, and then do the derivative of the second, but the derivative of e to the x is just itself. These two cancel, and I think we end up with just 5e to the x. Could we have done it in a faster way? Certainly. 5e to the x, 5 is a constant. The constant has no effect, it just hangs out. And then we just say, what's the derivative of e to the x? It's just e to the x. Cool. Done. Same answer. But something kind of weird happens when you go to take the derivative of e to the x when the power's no longer just x. Oops, this should say longer, but I will fix that next year. What about, for example, y equals e to the 2x? Well, somewhat strangely, the derivative is not itself. E to the x is the one that gets that cool derivative. Once you start changing the power, things happen. We actually know enough, though, to find the answer here. And to do that, we're just going to use our quick knowledge of exponents. And our knowledge of exponents says that if you have e to the 2x, you can actually split that apart, right? Because e to the 2x is really e to the 1x plus 1x. Wouldn't you agree 1x plus 1x is 2x? And once you see two exponents adding, then you might remember that that's the same thing as, and I don't need the ones in front of the x's, you might realize that's the same thing as having the same base but multiplying, because with the same base you add the exponents and x plus x is 2x. Well, how do we didn't know the derivative of this. We do know the derivative of each individual piece here, but they both have x's in it. That means two separate functions. Oh, the product rule. We got this. We know we're good at the product rule by now. So here comes our product rule. Derivative of the first, and then keep the second function the same. Now, keep the first function the same, and do the derivative of the second. And you're like, well, that's silly because e to the x is its own derivative. There's just lots of e to the x's here. And you're right, there are. So let's combine some like terms. Same base, so we add the exponents together. 1x plus 1x is 2x's. Same base, so add the exponents together, e to the 2x. And then, well, now that we're adding the same base, can we combine the powers? Well, no. Whenever you add terms together, you focus on the coefficients. There is one of these e to the 2x's plus one more. That means there are two of these e to the 2x's. Looking pretty good there. What does that tell us then? It tells us that the derivative of e to the 2x is 2e to the 2x. Let's try another one. the derivative of e to the 3x. Now, one option here, and I'm always really impressed by people when they come up with this, is people say, well, couldn't we do e to the x times e to the x times e to the x and do the triple product rule? We learned that on the previous page. Sure, that's awesome. Do the triple product rule, you'll get the right answer. It's not even that much more work. It might be the same work. I was going to be a little more sneaky and say, let's just split it into two terms. Let's split it into e to the 2x and e to the x. Because if you add the base, 2x's plus 1 more x is 3x's. And we know the derivative of e to the 2x now. That's over here. So I think the product rule comes out pretty nicely. E to the 2x, we'll do this one in purple, the derivative of e to the 2x is 2e to the 2x. I know that because we just did it. And then we keep the second one, e to the x, the same, plus, now keep the first one the same, that's e to the 2x, and take the derivative of the second one, that's e to the x. How do we combine these? Well, e to the 2x is multiplying by e to the 1x, so add the exponents, keep the coefficient hanging out. 2x's plus 1x is 3x. Same base, so add the exponents. 2 plus 1 is 3. Can we combine these? Well, I think we can. We have 2 of them plus 1 more. I think that gives me 3e to the 3x. So this one right here is 3e to the 3x. Well, why don't you pause this quickly, and taking a look at those two results, I bet you could actually do all of these problems down here now. Maybe not, but you probably can. So pause it, try them, unpause it, and then we'll see how you did. Alright, the derivative of e to the 4x, we could go through the same process as above, but look at this pattern. Whatever the power was up here, it did stay the same, but then that power also ended up out front. There is a 3 here, there's a 3 at the end. There's a 4 here. Well, I bet you probably came up with the fact that the derivative is going to be 4e to the 4x, and you'd be right. So the e to the whatever to the kx power is staying the same, but whatever that power is comes out front. Well, what if we did something like this? 3e to the 2x. We know the derivative of e to the 2x. Again, that's in purple up above. Is the 3 really doing anything? No, it's a constant that's multiplying. So sometimes you'll see it written like this. We're like, oh, that's multiplying. Let's bring the 3 out front and then just do the derivative of e to the 2x, because we know multiplying by a constant doesn't change our answer. All right, well, what is the derivative of e to the 2x? Well, it's itself times the power, right, times just the 2 in the power, and we end up here. Finishing this off, 3 times 2 I think gives us 6e to the 2x. And you probably could have done this even faster in the future then. You would basically say it's itself with this little coefficient times 3. What about this last one? We have 3 times x times e to the 3x. Couple ways to treat this guy. You could think of this as 3 functions, triple product rule. You could think of this as 3x times e to the 3x. Or you could do what we did on the previous one and take the 3 out. And since that's the last thing I wrote, that's probably what I'm going to do here. I'm going to factor that 3 out, and we're just going to find the derivative of x times e to the 3x. This has got to be, however, 2 functions multiplying. Both of them have x. This has to be our product rule. So 3 times, then I'm going to do a big bracket. You could do a big set of parentheses. I'm already going to have parentheses in here, so I like to switch up if I'm using brackets or parentheses so I don't confuse them. Let's go ahead and tackle that product rule. Derivative of the first one first. Derivative of x is 1. Keep the second one the same. All right, that's easy enough. Plus, keep the first one the same. Okay, I can do that. And now do the derivative of the second one, and that is e to the 3x with an extra 3 out front. And then close your parentheses. Is there anything these terms have in common that we could maybe factor out to hang out with the 3 out front? I think they both have an e to the 3x in common, actually. So let's take those out to hang out with 3. Give 3 some friends out here. 3 and then e to the 3x is factored out. What do we have left inside? Well, there's still a 1 here, plus, and there's still an x and a 3, so 1 plus 3x, I think. And that looks like a very nice answer. So, long story short, if you are asked to take the derivative of e to the kx, it's easy. It is still e to the kx, but whatever the k is has to come out front. The last page of this is some FRQ practice without a calculator. We're going to see what one of these might look like on an actual test, because you know your test has some multiple choice and some free response, FRQ, free response questions. I would ask please that you try to do these without just listening to me talk you through them. So take a quick second, work through it. If you get stuck, work on through the rest. And then once you've done everything you can, unpause the video and we'll take a look. Hopefully you've had some time to work through this then. Let's take a peek. Find the values of x for which the slope of the curve y equals f of x is 0. Alright, so this is where they start to use this notation again. What they really mean is where we have an output called y, we have an input called x, and then we have stuff that's happening to x, right? Remember, f isn't a variable. F is telling us that there's operations being applied to x. It might be multiplied, added, subtracted, square rooted, who knows? Okay. Well, they're asking about the slope of the curve. And in calculus, at this point in your career, if you are asked to do a calculus question and you don't either use a limit or a derivative or a theorem, you're probably doing something wrong. Most of this unit, most of the semester is about derivatives. There's a good chance you need to take a derivative somewhere. So I'll even go further. Not only do you need to use a limit or a derivative or a theorem, I'm going to even eliminate the limit part because that doesn't happen too often. And I'm going to say you either have to take the derivative or reference a theorem. And this doesn't seem like a setup for a theorem, so I would say for pretty much every problem in this unit, you should probably start by taking the derivative. So let's do that. Let's take our f of x up here and take the derivative. So f of x equals x times e to the 2x. And the derivative, I think our derivative here probably needs that product rule, doesn't it? We have one function times another function. Let's get to it. The derivative of the first is 1. Keep the second the same. Plus, keep the first one the same. And multiply it by the derivative of the second. E to the 2x does stay the same, but we need that k factor out front. Looks not too bad. Now find all values of x for which the slope of the curve is 0. Well, how does our derivative help us with this? Well, our derivative has an input and an output. Remember, and I'm going to erase this quickly, our input is still x, and x is just a value on the x-axis, right? If you have your xy axis, it's just something in. However, what does the output represent? This output over here is f prime of x, the derivative, and remember that the derivative is what measures the slopes on this original equation. So if you input an x over here, then the answer is going to tell you about the slopes of f of x. And here they're asking what value of x, so we don't know x, we don't know the input, what value of x is going to give us a slope of 0? Well, f prime of x is the slope. So what they're really saying then is, please set 0 equal to e to the 2x plus x times, well, let's rearrange this, sounds funky that way, 2x e to the 2x, and solve that equation. Solving this equation seems gnarly. I always look for factors if there's a bunch of terms in here, and I think these two terms have e to the 2x in common. So we're going to jump down here, we're going to say 0 equals, I'm going to factor out e to the 2x, and that leaves me with 1. We need a placeholder here, right? You even saw the 1 back over here if you wanted it. And then plus 2x. Once you've factored, if your two factors each have a value of x, let's use our zero product property, which of course tells us either 0 equals the first factor, which is e to the 2x, or 0 equals the second factor, 1 plus 2x. I think 1 plus 2x isn't too bad, right? I think here you're going to subtract 1, divide by 2, x is looking like negative 1/2. There is one x value that will cause the slope to be 0, because this x value, when you substitute it into your derivative, will cause the derivative to turn into 0 because we found it by setting the derivative equal to 0. The second one's a little trickier. We might need to remember that to undo e, we do natural log of each side, right? That's the inverse of e. These two cancel, 2x equals natural log of 0, natural log of 0, natural log of 0. I'm not remembering that off the top of my head. However, you could approach this from a different way and say, well, this is a number, 2.7, maybe call it 3 for now. 3 to what power is 0? Well, 3 to a positive power is going to be a positive number. 3 to a negative power is going to be 1 over 3, not 0. And 3 to the 0th is going to be 1. Oh, you might remember that there is no number that we need to use this year. When you make it the power, you get an answer of 0. Or even better, you might remember any log of 0 does not exist. Which means there's never going to be an x that will make this turn into 0. The only answer here is negative 1/2. Part B. Explain the meaning of your answer to Part A in terms of the graph of x. Ooh, that's interesting. So we might say on f of x equals x e to the 2x at x equals negative 1/2, the slope of f of x equals 0. Another way you could maybe say that is, I'll use some air quotes here, right? At x equals negative 1/2, there is a horizontal tangent line. Because remember, horizontal lines have a slope of 0. We found the only spot on f where there is a slope of 0, so there would be a horizontal tangent there. Moving on to 2. Let the table below, tabular data, very exciting, show derivatives of two continuous functions. Their derivatives are also continuous. Awesome, awesome, awesome. Evaluate the following derivative. Well, we need to take the derivative of these two multiplying and then plug in 1. We cannot plug in 1 first because that's a constant then. Those are numbers, and the derivative of a constant is always 0. We always need to find the derivative function first, then evaluate. This to me just looks like the product rule. That's exciting. So product rule, we get f prime of x, g of x, right? It's just typical straightforward product rule. F of x, derivative of the second function, evaluated at x equals 1. Which means we just replace all the x's with 1. I don't think I need to go too parenthesis happy here. F of 1, g prime of 1, and then let's fill everything in. F prime of 1, well, we take an input of 1, go to f prime and say, cool, that's 3. And then g of 1, that looks to be 4. Plus f of 1, that looks to be 5. Be nice if the next one's 6, 3, 4, 5, 6. That'd be a pretty fun pattern, right? But I don't think it's going to be, unfortunately, and I haven't used green. We're going to do g prime of 1, and that is 2. So I think we're looking at 12 plus 10, which is 22. Last but not least, let h of x equals f of x times g of x. Is there a value c on the interval 1 to 2 such that h prime of c equals negative 25y or y naught? Is there a value? Notice it didn't say find a value. It says, is there a value? Is there guaranteed to be a value? Ooh, guarantee a value? That is, of course, going to be a theorem. We know two theorems. We know the squeeze theorem, and the squeeze theorem is the one where you have three functions where one is in the middle of the others, and it tells you something about the limit of g of x, right? It says if these two limits are equal, then the limit at g of x is the same as those limits, but it definitely involves the limit as x approaches some value of g of x. I don't see any limits here. They're not asking us to guarantee a limit value, so I think that probably brings us over to the IVT, the intermediate value theorem. They're trying to guarantee a value on h prime. Well, this is a little bit different. We're stepping up the IVT here. We have h of x, but we're not trying to guarantee when we plug c into h of x is 25. We're trying to guarantee when we plug c into h prime it's 25. Well, the nice part is h prime of x is of course going to be the derivative of the right side. If we do the derivative of the left, you do the derivative of the right, typical algebra. And we already found that derivative using the product rule up above. So h prime of x is going to be f prime of x g of x plus f of x times g prime of x. How does the IVT work? Well, the IVT works if you look on this interval and the outputs of the endpoints border what you're trying to find, border this output, then it's going to work. So I think we probably need to find the outputs of the endpoints, right? H of 1 and H of 2, those are the two endpoints. So in the interest of space, I think we're going to go through and let's see. H of 1, oh, we already found that. That was so nice. H of 1 up here, that's when we plug in 1, is 22. Nice, less work. Let's go ahead and do the second one. We're going to have to do f prime, now we're working with 2 here. So f prime of 2 is 5, very cool. We have to do g of 2, which is 2. Then we need f of 2, which is 4, and g prime of 2, which is 4 as well. And if we do the math here, that looks like 10 plus 16 is 26. We need to probably just quickly verify to ourselves that the hypothesis is met. Is 25 this output in between the outputs of the endpoints? Yes, it is. So you'll notice that we're starting at like the 22nd stair and we're climbing up to the 26th stair, and assuming that we touch every stair in between, we will definitely cross over the 25th stair. How do we conclude? That's always the tricky, scary part with these. Well, we need to make sure the hypotheses, criteria are met for this, and then our conclusion's easy. So let's begin. As h of x is continuous. Every single theorem we do this year should start with as the function is continuous. But then pause, question yourself, is h of x continuous? Well, there's a couple things wrong with this. First, h of x is continuous because they told us that f of x and g of x are continuous. However, second, we don't care about h of x, we care about h prime. And so I probably should have been much better with my notation over here. I found h prime of 1 and h prime of 2. That would have been bad, definitely would have lost points there. And so we don't care that h is continuous, we're trying to guarantee that h prime will cross something. So I need as h prime is continuous. But wait, we only knew these functions are continuous, so h prime is kind of made up of those functions. But what about g prime and f prime? Are those continuous as well? Their derivatives are also continuous. Sneaky, sneaky, we did need that. So now h prime is only made up of adding and multiplying continuous functions, which means h prime is continuous. Again, don't have to prove that, but it's always good to prove to yourself, because sometimes they throw you off and it's not continuous, and then you can't prove it. So, as h prime of x is continuous, and what else had to happen for this to work? Well, this output had to be between these two. So, and h prime of 1, that's the small one, is less than 25, which is less than h prime of 2, showing that 25 is between the two outputs of the endpoints. Then, now we're on the easy part. Then the IVT, let's rewrite. We can say shows there is a value c on 1 to 2 such that h prime of c equals 25. Again, just rewriting what's already there. And we're set. Always good to keep those theorems up to practice. We only learned 5 of them that we're going to have to apply this way for the year. It's nothing too terrible. So thank you for getting in your practice for the product rule, our multiplication rule, and e to the kx. Wish you the best of luck. Don't forget your independent practice, and I'll see you back here for your next lesson on the quotient rule.